Okay, this is our last presentation before interactive panel, and our presenter is Rimantas Zukaitis. He is a senior system architect from a company who provides insurance services from Lithuania. And Rimantas presented previously, and his presentations were very practical. And he right now leads a team who is developing, I believe, R&D project with the goal to teach LLM to write business rules. Very interesting goal, and let's see the preliminary results.
Yeah,
go ahead.
So I will talk about it's more like my personal journey on trying to teach LLM to understand our rule engine, which is the engine itself, it's open source, but most of the metadata around it is internal. So the goal of all activities, as everyone is moving to Gen AI and agentic coding, the goal is use AI to speed up implementation of business rules, as this is perceived as time-consuming and error-prone process. Typically, developers are afraid or unwilling to spend time, and so this, in our context, this is the place where we want to improve. So shortly, what we're talking about, as I am team lead and architect behind Kraken validation rule engine. So it's a bit different from what most of the presentations are. It's not the typical decision engine, but more of using notation of business rules to validate the data in the main model. So it's kind of a middle ground between full-blown rule engine and constraints engine. It's like very relevant to insurance domain, where we have a lot of variability between the rules depending on various insurance providers, states, regulations, etc., etc. So in our case, the rules are defined directly on the domain entity model, so there is no mapping, no preparation. So that gives very tight integration, and there can be multiple rules in the same attribute, and there can be hundreds or even thousands of rules. Typically, we are covering majority of attributes in the domain. They can be of varying complexity, starting from simple rules, which say that this attribute should be hidden or mandatory, going to very complex expressions. And the major benefit from this is that we are using the same rules to validate both on the backend, on the server side, but also on UI, on the rich client, which allows us to reuse the same implementation in two places. And like I mentioned, there is an engine itself, but to make it convenient for developers to use and integrate into existing applications, we have very elaborate integration layer, which is causing some of the problems with using it in AI. So again, as a very simple example of the rule. So in this case, we have rules are identified by name. We're defined on the entities in the domain model. And each rule is bound to a particular attribute. Those rules can be conditional or unconditional, and they can have various what we call payloads, or rule types. So it can be validation, default value, presentation, which affects how this attribute behaves in the UI, etc., etc. And there is like hierarchy and dependency resolution. So we can have dependencies between the rules. We calculate which rule should be executed first, in order to get consistent execution results. So the idea, again, the part of the complexity is that those rules can be defined on the attributes on the domain, but we can reference different attributes from the whole domain model. The rule engine provides the discovery of the data and automatically injects necessary values. So this gives somewhat flexibility that I can define rule, for example, on risk address without knowing how it connects to the rest of the domain. I just say that it should be applicable on this particular entity and should fetch data from other entities. Yeah, so that's very quickly what we're dealing with. Like I mentioned before, it's a bit different from traditional DMN models. Well, not a bit, but quite substantially. And this is the problem because we would say that it should be very easy. We need to teach the model to generate these DSLs, and that should be fine. But it's not so simple because at first, it's not only implementation. When developer is implementing a rule, it's not only implementing the DSL itself. You need to understand what is existing product configuration, how this rule maps to the data model, on which entities it should be applied, etc., etc. How these rules, what rules are already implemented, maybe on that attribute already rules which would conflict with newly implemented rule, and how other downstream artifacts are affected. So if I'm adding a new rule, maybe it will affect UI behavior, maybe it will affect the downstream service implementation. Maybe if I'm validating something or changing some values, this will affect how the system behaves. So it's not only producing the DSL itself or implementation. In similar fashion, like modern development, it's not only typing code, it's a lot of analysis and understanding what's there. It's a similar rules implementation. And that's where the problems start to arise because the model needs to understand all those concepts. Also, the rule definitions themselves were not in isolation. They depend on a lot of different artifacts. So the rules, we're leveraging our expression language, which again, it's a separate DSL grammar with separate keywords and separate syntax. Then on those rules, typically developers are implementing unit tests, which the approach which I presented a few years ago in this conference. The same rules can be loaded from decision tables. So if we have a lot of repetitive rules, we can provide them in compact form in the table. And then from this table, the rules are generated automatically in the runtime. And like I mentioned, there is domain model on which basically defines the data structure in which rules will be executed. There is versioning model, which says how those rules should behave when certain data, which we call dimensions, changes. So for example, how we're applied when effective date changes, how we're applied on different packages, on different plans, etc., etc. And all this is tied with rules project model, which is again a separate DSL artifact, which kind of connects all those various artifacts. So when developer needs to implement a change, the problem is that these changes often span across multiple of those artifacts, and LLM not only must understand the syntax itself and how to make changes, but also how these artifacts are interconnected. So, for example, a typical use case would be that the task says that for a particular product, we need to update the product, add additional coverage, add a new attribute to this coverage with, for example, 20% limit amount value for California state and for 50% for any other. And also limit amount values between 100 and 1,000. It's a typical task, which again includes changes to the rest of the configuration, but also changes to the rules. Typically, what happens when developers are implementing it, we break down these tasks into separate subtasks. So somebody will be updating the domain, testing the changes, when adding the rule, then testing that rule, maybe implementing tests if the rule logic is complex. So that's what we need to replicate with the model. For example, in this case, we might already have some entities and types. So in this case, we are adding a new entity, which is extending existing what we call base type. It's a representation of interface. We're adding new attributes. Again, we have a syntax which allows to specify only new attributes. The rest is inherited from parent base type. So the model needs to understand all these mechanics. And when we were defining rules, so somebody could implement and say, okay, I have the 20% of on the California, and again, type it should be 15. But for example, I have different value for not California, so I might implement mutually exclusive rules. But typically, what we would do, we would define a rules version for California with dimension attribute, and then the engine would resolve different rules implementations on depending on what the state is. If the state is California, this rule should be taken. If this, then it should be this one. Again, sorry for the typo. So the problem is that we need to teach the model both to understand how these artifacts are used, so the syntax, semantics, and relationships. But in addition to that, we need also model to teach to understand what is already implemented. In a similar fashion, like we are using a coding agent, the model is able to read existing source code, understand what is in the source code, and make changes. So the same problem is here, but it's not only teaching about the syntax and about the semantics and relationships, but also teaching how to interpret what is already there. And that was a kind of a problem, because when models are working with publicly available languages, we already are trained on a lot of samples, and we know how to interpret that information correctly. In our case, we need to do both. So how we can do it? So basically, the model itself, it is just token prediction machine. So we provide the text, and despite how complex and big model is, what it does, it predicts next token. Then it adds that token to existing text and predicts next token, etc., until there is like a stop token, then it provides answer to the user. So the model itself cannot do this, and the model itself is trained on the static data with like knowledge cutoff date. So at a certain whenever the vendors are training the models, we are taking the data up till a certain date. So that means that first of all, even if all the specifications and syntax and etc. would be public, and due to some lucky occurrence, it would be taken into training corpus for publicly available models. The second part, which involves that we already have some implementation on machine on developer environment, it's not going to work. So there are two cases how we can do it. First, we can put this additional information to a model itself. So either train the models from scratch or fine-tune one of existing open source models, or pass to the model during the runtime. So again, I will try to cover the journey through all of those options. So building your own model is something which sounds very, very complex, and it is complex if we want to reach the state-of-the-art model capabilities. So it's very expensive. It's probably in tens or hundreds of millions of dollars. It's insane amount of data. So some of the vendors are boasting that we are using all the textual data ever produced by humanity. It's like 10 to 14 tokens. However, like a few years ago, emerged a concept called the small language model, which typically are up to 10 billion parameters. And in literature, there were a lot of cases where those models could be trained or fine-tuned for specific DSLs, especially for niche domains like specialized DSLs for example, describing hardware and electrical schemas or SQL or whatever. So this was one of the areas we could investigate. So it's much more affordable compute-wise. So 1 to 3 billion parameter model is actually doable on rented GPU cluster. It could cost them like tens of thousands of dollars. If that would be the case, it's quite doable and affordable to a certain degree if there is a need. And there is also lots of materials and examples, especially over the last year and a half. And probably the best place to start is Karpatis NanoChat tutorial, where he basically is explaining how to build model from scratch. And it's just good read in general to understand how a model works. So what he's stating that you could build like GPT-2 level model in for like, I don't know, several $100s typically. Again, but that's still quite expensive and huge undertaking for free time. So it requires a lot of data. Even for like 3 billion parameter model, we need like 30 to 60 billions of tokens. And the problem is that a significant portion of this data should be curated domain-specific data sets, typically pairs of prompts and responses, which again is probably orders of magnitude more than everything we had in all our repositories for Kraken rules and all related metadata. It's just a lot. And the problem is that it's good for single localized niche DSLs, but in cases when we have multiple different languages and when we need complex reasoning, first of all, for complex multi-hop reasoning, the model will not be capable enough. We need definitely much more parameters, and it will be lacking in generic tasks. Probably if we would start with from scratch, we need few iterations, which again multiplies costs. And one of the biggest problems, even if we would invest all that money and provide this model, regardless on how good it would perform, the problem is that the rest of our framework is still evolving and we're adding new features. That means every time we're changing grammar and adding new capabilities, we would need to retrain the model. That means we need to invest all that money again. So the cheaper option is to fine-tune existing models. Again, there is a lot of materials, and typically there are two approaches to do full fine-tuning. So it still requires a large and high-quality data set. It's probably in tens of thousands of pairs. For more complex DSLs, it could be in hundreds of thousands. It still requires like a lot of computational resources. So if we're talking about, I don't know, 10 billion parameters, so that would need like probably 40 to 80 gigabytes of video RAM just to start with training. Another option which became very popular recently is LoRa and quantized LoRa. So what we call parameter efficient fine-tuning. So it's kind of optimized and it works on more smaller data sets, and especially quantized LoRa, as it works with quantized version of a model. It works on smaller video RAM requirements. So it's lower training cost, but it results in slightly lower quality, especially if we want like drastical behavior changes. This approach might be not enough. So as an exercise, I tried to do this for one of our core DSL's expression language. So just to train the model to write expressions which are capable conforming to the syntax. Again, that was a year and a bit ago, so I took a Qwen3 model and used 4-bit quantization. Still, it required significant data set of around 1,000 pairs, which was probably the most painful part of exercise. So the results that the model kind of gained the knowledge to understand and implement those expressions. But still quite high hallucination percentage when the prompts were different from what was in dataset. So, for example, if the prompt is formulated slightly differently, it might miss the target. Again, this model was purely, since it was small, it did not have any reasoning and tool calling capabilities, and it's specialized only to expression language. That means that expanding across all the DSLs we need and to understand all those interrelationships. When we need a bigger model, we need exponentially more data, and it becomes more expensive. And again, there is still problem with retraining. So I did a few iterations. One iteration, it's like up to 12 to 24 hours. So it's still quite computational expensive. So if training is not an option, even it was quite fun exercise, another is just use input context. So this is how all the industry is now using those models. This is how whole agentic approach is working. So typical LLM invocations, like I mentioned, it just predicts the token and the next token, and typical interfaces you following the chat model, that there is like a system role, assistant role, and user role. So there is a user prompt, you send it to LLM, LLM returns the response with assistant messages, and it kind of goes on, and all this chat history accumulates in the context. So what is in the context? It is available for a model. So it's like king in this place by dictating the model behavior. But the problem is that it's limited to a certain number of tokens. And even the bigger problem is that it's prone to the context phenomenon called context rot, that once it reaches certain amount of tokens, the quality of answers starts to degrade quickly due to attention algorithm implementation specifics, which is like quadratic complexity. But yeah, the general approach is that if we put some external knowledge into the context, this should be available to LLM, and then LLM can make decisions based on that information. So there are various techniques which evolved over time, and let's quickly review them and see how we fare. So the simplest case, it was just nothing. When ChatGPT appeared, it was purely static. It didn't have any capability to call tools, etc. So even then, we could try to ask it to implement Kraken rules about which it has no knowledge. And yeah, it's more like a joke exercise. Response is pure hallucination. Typically, it varies a lot depending on what you ask. And the biggest problem was that model doesn't know how to say, I don't know. It still tries to provide and please the user and provide like good example. So in this case, when we prompted to implement the rule from example before, it provided something completely different, which does not have any relation to the syntax, and it's just like that. And when prompted again, it could vary between those syntaxes completely on random. So the next stage, which probably appeared right after that, was like prompt engineering. So users quickly realized that you can still manipulate LLM behavior by providing different information as part of a prompt, and different techniques appeared. So you could pass this new knowledge as part of a system message, or you could pass it in your chat history, or have a dedicated block for the context, or again, there were like different methods. Few-shot prompting was very popular, where we provided few examples, and based on those examples, model tries to infer what you are asking. The chain of thought was also very popular, where you ask the model just to think about how it could be implements this, and then this message is used as part of the history, and when model behaves much more predictable. This is what gave rise to the current reasoning models, where the model by itself generates all this chain of thought as part of often invisible to user, but it's added to the context, and that provides more precise results. Again, role prompting, you could say, pretend that you are an architect who knows how to implement this and that, and again, schema-guided prompting. So in this case, it's better results. So for example, what we could do in this case, we could upload together the prompt, and as the grammar description for the DSL provides some instructions how this should behave. So it provides better results, but it's kind of hallucinates us a lot. It's poor reproducibility because it's not very usable, because nobody will use a chatbot and paste every time all the metadata and all documentation how to implement rules. And again, back when the context window was limited, so you could put only the limited amount of knowledge. And again, if you're providing only the syntax and instructions, that response will not see what's already implemented in the rules on your system. So it's kind of, again, toy exercise. So for example, if we provide all the grammar and model interprets the syntax correctly, so it provides the rule which follows syntax that matches the grammar to a certain extent. But as it doesn't know anything about the domain model, well, it kind of attribute name is incorrect, the condition is incorrect, etc. So it's kind of hallucinates. And again, back when it was also more like an exercise, just trying to show what it could do. So the next approach was when we added ability to upload the documents. So you could create a workspace in your chat assistant, upload some documents. And it was advertised that all those documents are part of the context, so you don't need to add them to the context by manually. In reality, it was most often RAG in disguise. So it's, again, with its pros and cons. It should have simplified context knowledge handling, but it was more useful for day-to-day tasks like summary of a document, search, etc., but not for code generation. So now we're stepping to a second iteration where we are not using the chat assistants, but trying to use API and implement workflows with various frameworks. So the most popular and simple approach to extend LLM was retrieval augmented generation, where it allows to provide new information based on your queries. The idea is that you index your documentation. So these documents are broken into chunks. Those chunks are stored in vector database. And then when user provides a query to the LLM, this query is compared, calculate embedding for the query, with queries compared to what is in the vector database when you fetch with similar chunks and inject them into context. So it's kind of automatic way to find similar data. Yeah, so it's kind of good that you could reuse existing artifacts. So typical approach probably would be like export data from the wiki, feed it to the vector database. Again, it kind of worked to a certain extent, mostly that due to the paradigm mismatch. But this approach was invented back when the context was very limited, up to like 8,000 tokens, when 16,000 tokens. So that's why you would chop the information into the chunks. So you cannot upload the whole document. You just pull out the document, the chunks which are similar to a query. Which is again which is good when you're working with like generic tasks, when you need to find something in a document, do some summaries, etc., etc. But it's not working very good when you have like structured information, like specifications about rules and DSLs in your wiki, and then you try to find information just purely by vector search, because your prompt could be implement rule blah blah blah, and this prompt will not be similar in vector store to the data you need to fetch. And again, it's good only for static data. If you will try to put code from a developer machine into vector database, then you need to reindex it. And again, it becomes very complicated very quickly. So yeah, I don't have example for this, but it kind of was similar to what we had with this. So the next approach, which we replaced with quite quickly, was that vendors started initially providing ability to do tool calling. So the tool calling was the idea that you allow a model to do some action, to request to do some action. So when you call the model from your client, you inform what tools are available. Then model can request to execute the tool with certain parameters. So client executes that tool, provides the answer to the model with second request, and then model do this some deliberations and returns the response based on the tool results in the prompt. So that was quickly followed by MCP standard, which became very popular for standardizing the packaging and invocation, because the tool APIs were all different by the vendor, different by the actual tool. So it was kind of difficult to manage. MCP quickly exploded and started providing MCP servers for all possible cases. So it's quite good. And frankly, it was much better performance than retrieval augmented generation, especially for this case. So, for example, using MCP server connected directly to Wiki and outperformed our initial retrieval augmented generation implementations quite better, because even with the search tool from the Wiki, modern models managed to fetch information much better than all optimized retrieval augmented generation pipelines. But implementation still for workflows is very good, but for code generation it still like requires a lot of custom orchestration, especially when we're talking that we need to access all the code on the developer machine. So even if we have ability to invoke the tools, if we want to access what is already implemented in various DSLs and in Java, in some cases, we need to provide this. So instead of reusing this, we can just reuse AI coding agents, which basically have all those capabilities inside with tools like Cloud Code, Codex, Copilot. So the benefit is that it's already tailored to work with code. It already has all the infrastructure to fetch the files, etc., and orchestration to fetch what and how is flooded to model reasoning. This is especially exploded around the new year when the new generation of like agentic optimized models, which were like trained to do this reasoning, appeared. So when we have like ability to provide this external knowledge to the agent, so default approach is either using AgentsMD or ClaudeMD. Again, in these files, we could provide only limited amount of data, but we can instruct how this data should be loaded. So this would be a tipping point in terms of performance, where all those experiments went from the like fun and games to actually something useful, because all the heavy lifting could be done by the model. So, for example, if I have like a large number of rules and I did some changes in my domain and I need to update all the rules, it's like fairly easy to do for a model and quite effort intensive for the person. The problem was that it's still like complicated to set up, because you would need to do per project setup or per developer setup depending on the approach. It's quite expensive and complicated. It's error prone, and accuracy again depends on correct setup. Again, the other part is high token costs, because differently from what we have in workflows or in chat applications, these agentic loops typically cause a lot of requests to the model. So you might prompt it once to do some changes, and that could result in like 10 or 20 subsequent requests to the model, because it does some action, loads the file, sends this file to the model, and then gets some instructions, etc., etc. So the problem is that the context window fills up very quickly, and you're paying for those tokens with each request. So if the agent does like 20 requests for 100,000 tokens, usually you will use up 2 million tokens. And again, as the context window fills up very quickly, even with modern models, the issue of context rot becomes like quite significant. So you need to balance this. So in this case, for example, like I mentioned before, the accuracy becomes quite okay in some cases, and this is example from previous, but if we do not have instructions that it should use dimensional rules, it would implement rules like just with mutual exclusive conditions, which are difficult to maintain. So the accuracy still it kind of becomes quite okay, and now we're switching to the point how to do this reproducible and scalable across across multiple developers and multiple projects. So one of the approach we reviewed was spec-driven development with using OpenSpec framework. So it uses memory bank concept, which says that your project context, architecture, coding standards, all the instructions, they are stored in like what we call memory bank. So it's a set of .md files. And this framework knows how to query those MD files and how to provide hints to the model how to behave them. So these memory banks both stores like the grammar and instructions how to use our frameworks, but also pre-generated metadata about the project itself. So it says if you will be implementing rules for the policy and the writing, then you should go to this Maven project, find these files, and it will be in these files. For this particular rule project, the domain is in a different project, and you should inspect this file. etc., etc. And that works really good for the models because this framework kind of orchestrates how the data should be fed. So the outcome is that it's reproducible and context-aware setup, which is fairly quickly. We implemented some developer tooling, which like pre-generates all the necessary data, either from our artifacts in specifications or from the project structure. And it kind of on par with mid-level developer for lower medium complexity tasks. Yes, if you need to have something very specific, maybe it's still kind of can struggle, and probably will struggle not due to model complexity, but because the instructions do not cover these cases. But that's where we started to understand that it's probably usable and to automate this. The side effect is that this memory bank became quite big, so only for the Kraken rules, it became almost like 150K in total of the memory bank. Again, this OpenSpec framework loads it by chunks, but it's still kind of complicated. And as we have multiple teams and multiple domains, it probably scaling across all the stack would be quite expensive and just result in the context load. Another problem is that you need to maintain this memory bank as the stack evolves. So that means that all the documentation we have in our official documentation needs to be synchronized and maintained in these memory banks and these generators, and then we need the ability to version it, etc., etc. So it kind of logistical problems. Yeah, but ideally, this results in quite what the typical developer would implement, because we can provide instructions and say that if you have rules which are like varying by values which are part of dimensions on the entity, then you should implement in this particular way. Yeah, so the next logical step was refactor all this memory bank approach and introduce skills, which again is probably the latest trend and fairly successful one. So the idea is that we are not having like a single big set of instructions, but we like refactor this into targeted skills for particular actions and particular teams. So these are much more easier to set up. They are reusable across different cases, so we do not have a problem when same behavior needs to be in different use cases. Those skills are loaded in demand dynamically, so we do not have immediate impact on context size. As only skill description is loaded on initial invocation. And yeah, we decided to distribute it as binaries as part of a component. So that means if a developer is adding dependencies to use our Kraken engine in the application, it automatically will set up all the skills. Yeah, so far that gives the best performance and accuracy. It scales better, and it can be introduced incrementally, as opposed to this memory bank approach where you have to provide everything at once. Maybe a problem is that, again, scaling across multiple teams and multiple domains, amount of skills can grow quite quickly. There is a composition overhead when you, for example, you say that in order to use the skill to write rules, you need to load the skill which understands the domain model, and then you need to load the skill which understands the versioning model, etc., etc. So eventually, for those cases, it still can have overhead. And by the design, the triggering of those skills is not deterministic. So the model loads the descriptions and then decides which skills to trigger. what we decided to do instead, that when we have dependent skills, we just instruct that if you're using this, load this skill as well, because you will need it. So it gives kind of better precision. Again, further improvements. So what we want to investigate, so maybe offload some of the work to deterministic tools. So agents as tool patterns. So maybe we can offload some of the behavior into separate agent loop and invoke it as a tool. So instead of like loading all those skills into the context in one go, we can spawn a separate agent which will do this in separate. Also, there is like this approach of micro or deep agents, which is now being popularized by LangChain, where we say that instead of like having one big context, you could invoke a lot of small agents, which basically, for example, if you need to implement 10 different rules or update 10 different attributes, you could do a single agent invocation for each change, which could deal with like very small context. Yeah, so we are coming to the end of presentation. So one phenomenon which is kind of side effect of this is what I call uncanny valley syndrome. So when we started like doing various experiments, especially with initial approaches with like ChatGPT and all those funny hallucinations, it was very funny because it's very easy to discern when the model is lying to you, because you see that the syntax is incorrect, or the variables are non-existing, or entities are incorrect. But the problem is that the more realistic the output of a model is, the more difficult it is to detect the issues. And I kind of draw a parallel to this phenomenon which was introduced in the 70s called uncanny valley for robots, where we said that when the robot is like humanoid but discernible and not similar to human, people accept it. But the more human-like the robot becomes, the more like disgusting it becomes, and the more like people become uncomfortable with them, until it reaches the you cannot discern from a human, then it's probably then okay. So it's similar with the code, that in first iterations it's kind of easy and obvious, but the higher quality is, the more disruptive and disturbing it could be, that you sometimes have to review the generated output, and you know that it was generated by the agent, and kind of it's in some cases it's visible that it's not human implemented, and for some people it causes like different emotions. Maybe it's also related to economics of the time, because when somebody is implementing something and spends like a week or 2 weeks on a feature, spending a day or two to review that work seems reasonable. But when the model can generate it like in an hour, then spending 2 days to review the code for some people seems like expensive. And there's always this like kind of allure to like either to accept it and say, well, look, it looks good for me, or just in some cases just to push back and say, I don't want even to deal with this. And again, that the changes and rewrites are very cheap now. They even make this problem worse. That the cheaper it is to implement, the more load it causes for reviewers.
Rimantas, you're running out of time.
Yeah.
Okay.
So
let's just see if we have a few questions. I will ask very quick questions, yes or no question. Can you generate decision tables?
Yes, we can. Currently, we have implementation for the decision tables, which we're using to store the Kraken rules. And yeah, we kind of have the skills to generate the syntax. There is no, as we are using GPU's decision tables only for very simple chat scenarios, we do not have a case where like implement the decision model in the decision table. But for example, we can say, okay, create a decision table to store all the defaults. And if you're adding default value rules, instead of using the DSL, add it to the decision table. So it's much more readable.
Okay. Anybody? One more question. Okay, thank you very much, Rimantas.
Thank you.
Good luck with your work.